One of the main tools of statistical process control, SPC, in quality control are the control charts. They are known as the voice of the process. Control charts were actually created by Walter Schwartz. He is actually known as the father of statistical process control. And he actually used for the first time the quality control charts for quality control. But what is quality control charts? A control chart is a time order plot and representation of sample statistics, for example, the sample means, obtained from an ongoing process. These are used to distinguish between random and non-random variability. So how does this work? For example, when you obtain the sample statistics such as the average, the sample means of a process, which is an ongoing process, so you're going to do it in dynamic, timely manner. And then the control chart is going to be built based on the sample average of the process, and there's going to have an upper limit and a lower limit, what are called as the control limits. So within these lower limit and upper limit, this is the acceptable change or variability. So for example, suppose that the red line is the sample mean here, and the upper limit, this is the upper limit, and this is the lower limit. So when you take the sample means, the sample representation, you can actually represent this by dots here. So some of them going to be in the upper level, some of them are going to be on the lower level within this range. So within this range from the lower limit to upper limit, this is acceptable variability. If it falls outside of this range, here or here, lower and upper, that's going to be unacceptable. That means that the process is out of control. So this is how this process, these control charts work. So here is a more clear illustration of a control chart. As you see, there is the main line is here, and the control chart has two lines, the upper control line and the lower control line. So within this range, the variability between upper level and lower level, that's in control. If a sample statistics value falls outside of this range, this is called out of control. So this is called, within this range is normal variation due to chance, and beyond this, lower or upper than this, it's going to be due to assignable sources. That means that you can actually identify a cause and assign the variation to that cause. And if you fix that cause, you can actually prevent this variation, this unacceptable variation. So each data point that you see in this control chart, each of these represents a sample of an observation. So for example, in a timely manner, every 10 minutes or every 1 hour, they're going to take a sample of, for example, thousands of items or hundreds of items, depending on the size of n, and then they're going to find the average of those, and they're going to show the average as one of these dots here. So there are four commonly used control charts. Two of these charts are for variables, and two are for what is called as attributes. You're going to learn about attributes later on. Attributes actually are those data that can be counted. For example, the number of defective parts in a sample, or the number of calls that you receive per day. These are things that can be counted, 0, 1, 2, 3. Variables, on the other hand, are data that can be measured, such as so it's in a continuous scale. It's not integer values. So such as the time that for a process that needs to be completed a task, or the length of a product, or the width of the product, or a height of a product. So these are measurable. These are called variables, but the characteristics that can be counted, these are called attributes. We're going to learn about these later in this lecture. As mentioned before, there are four different control charts. Two of them are for variables and two of them are for attributes. Let's just start with the control charts for variables. First of all, what is a variable? A variable is a characteristic of a data that can be measured in a continuous manner. For example, the length of a product, the width of a product, or the height of a product, or the timing of a process. There are two types of control charts for variables. One is the mean control chart, which is used to monitor the central tendency of a process. So it's going to use the statistical sampling mean of this process. That's why it's shown by X bar chart, because you represent the sample statistics with X bar. And the range control chart, which are used to monitor the process dispersion or the process scatteredness. These are shown by R charts. So we're going to learn about these two control charts for variables. Establishing control limits for control charts for variables. Here you see the two formulas for control charts for variables. We have the X bar chart for, this is for X bar chart. X bar here is the average of sample means, which is going to be the middle line, the central line that's going to be the central tendency measure. And that's just an average definition of average that we learned from statistics. X bar I here, they are the mean, the statistical sample means for sample I. So what you do basically is you have, suppose that you have k samples, and for each sample you have gathered whatever number, n number of observation. And you find, for each sample you find the average, that's shown by X bar I. And if you find the average of those averages, that's going to be the grand average, or X bar here. For the R bar chart, we're going to find the average of the sample ranges. So R bar here is the average of sample ranges, and Ri is the range of sample I. So you suppose that you take k samples. For each sample you identify and find the range of sample. That's the maximum variation minus the minimum variation. And then out of these all k samples, you find the average of these ranges. So let's see how these control charts work. Let's actually build and establish the control limits for them. Let's start with X bar charts control limits. As we mentioned, X bar charts are used to monitor the central tendency of a process. But every control chart must have a lower limit and upper limit. How do we find the upper limit and lower limit for X bar chart? In the previous formula, we computed the grand average, X bar. That's the central line. To compute the lower limit and upper limit lines, that depends whether we know the standard deviation of the process or not. Suppose that we know the standard deviation of the process, that's sigma. If that is known, the upper limit and the lower limit, control limit, can be computed using this formula. So the upper control limit is the grand average that we computed in the previous formula, plus z multiplied by sigma of X bar. Sigma of X bar is the standard deviation of the sample, which is equal to sigma, the standard deviation of the process. That's, if you remember from statistics, that's from the population, divided by a square root of n. And n is the sample size. So remember, n is the sample size. That's how many observations you have in a sample. you could actually have different number of samples. For example, you can have k number of samples. Each sample is contained of n observation. So n here is the size of the sample. How many observations are in each sample? Z that we have is the standard normal deviation that we're going to find from a table. So using these two formulas here, we can find the control limit, upper limit and lower limit. To best understand how the control chart X bar and the previous formula works, let's do an example. A quality inspector took 5 samples, each with 4 observations. So 5 samples, that's K, and 4 observations, that's N, of the length of time for glue to dry. The analyst computed the mean of each sample and then computed the grand mean. That's the grand average or X bar. All values are in the minutes basis or measure. Use this information to obtain 3 sigma. This gives you the hint that Z in the formula that we had is 3 sigma. Because if you look here, the formula for upper limit and lower limit is grand average X bar plus minus Z multiplied by sigma. So 6 sigma means Z is 6, Z is 3. 3 sigma means Z is 3. 6 sigma means Z is 6. So in this formula, we know that Z is 3. Use this information to obtain 3 sigma, that's Z equal to 3, control limits for means of future times. It is known from previous experience that the standard deviation of the process is 0.2 minutes. So you have the formula here, you have the information from this table here. So please pause, work on this problem, try to find and establish a X bar control limit and the upper limit, the lower limit, and also the central line. And after you're done, come back to see the solution. Let's solve the problem. So we have the table here. We have 5 samples, sample 1, sample 2, sample 3, 4, and 5. Each sample have 4 observations. So we need to compute the average of each sample, that's X bar. To do that, you would need to sum these up and then divide them by 4. So that would be, for example, x11 plus x21 plus x31 plus x41 and then divided by 4. So we already have computed, and the average for the first sample here is 12.1. So that's the average for the first sample. The average for second sample, we're going to compute it in the same way. That's 12.12, 12.11 for the third, for the fourth and fifth is 12.10 and 12.12. So this is x1 bar, this is x2 bar, this is x3 bar, x4 bar, and x5 bar. So the formula is for the X bar chart, for the upper limit control line, that's X bar bar, the grand average, plus Z multiplied by sigma of X bar. So, and for the lower limit, it's X bar bar, that's the grand average, minus Z multiplied by sigma of X bar. So what we need to do here is we need to compute X bar. We know that Z is 3, that's given from the problem, and we need to compute Z sigma of X bar. So let's go ahead and compute X bar bar. To compute X bar bar, what we need to do is we need to find the average of averages of each sample that we have here. So here, that means that we need to find the average of these averages. So that would be 12.10, that's x1 bar, plus 12.12, plus the third one, 12.11, 12.10, and 12.12, divided by the number of samples that we have, which is 5, divided by 5, and that would be 12.11. So the grand average x bar bar is 12.11. Now we need to find sigma of x bar. Sigma of x bar is sigma divided by square root of n. Sigma is given in the problem, that's 0.02. N is the number of observation, which is 4 here in each sample, so n is 4. So sigma of x bar is sigma divided by square root of n. That's 0.02 divided by the square root of 4, which is 0.01. So now we compute the upper control limit and the lower control limit. The upper control limit is grand average, that's 12.11, plus sigma plus z, which is 3 here, 3, multiplied by sigma that we found here, sigma of x bar, which is here, and that's going to give us 12.14. So the upper control limit is 12.14. The lower control limit is the grand average minus 3, which is z, multiplied by sigma of x bar, which we computed here, and that's going to give us 12.08. So now we have the upper control limit and lower control limit. So all of the sample means, now let's actually use it. All of the sample means have values that fall within the control limits, therefore the process is in control. Let's see. So now that we have the upper limit and lower limit control, let's see whether the information that we have gathered, the samples that we have, based on this we can check the quality control. We want to see whether the quality control is passed. That means that the process is under control or in control, or the process is out of control. That means that the variation is unacceptable for a sample, for example. So what we need to do is we need to, for each sample mean, we need to see whether these values would fall within the acceptable range. That's within the lower limit and upper limit. So let's start with the first one, 12.10, that is between 12.08 and 12.14. So that this is checked, is in control. We're going to go to the next one, 12.12. 12.12 is within the 12.08 and 12.14. That's the lower limit and upper limit. So the second sample is also checked, is in control. We're going to go to the next sample. So that's 12.11. 12.11 also is within 12.08 and 12.14. So is under control, is in control. The fourth one is 12.10. That is also within the control limit. So this is also checked. And the last one is 12.12, which is between 12.08 and 12.14. So this one is also in control. So all of the sample means have values that fall within the lower limit and upper limit, the control limit. So we can conclude that the process is in control. If you remember from statistics, practically we never know the standard deviation of a population. So it is rare that we know the population standard deviation. So let's go to the second scenario for X-bar chart control limits. If the standard deviation of process is unknown, which is more practical scenario, we would use the sample range as a measure of process variability, and there's going to be another formula as you see here. The upper control limit and the lower control limit is going to be computed using this formula. So the grand average is the same, X bar bar. The Z multiplied by sigma of X bar is going to be replaced by A2 multiplied by R bar. A2 here is a factor from a table that we're going to see, and R bar is the average of sample ranges. So let's see an example to see how this formula works. This is the table that you can see, find actually the A2 and also D3 and D4 that we're going to talk about it later on. So based from this table, you can find the A2 based on the number of observations that you have within each sample. So for example, if n is 2, A2 is 1.88. If, for example, n is 10, the A2 is 0.31. So this is the same problem as the previous problem, but with a different setting in which we don't know the standard deviation of population. A quality inspector took 5 samples, each with 4 observations of the length of time for glue to dry. The analyst computed the mean of each sample, that's xi bar, and then computed the grand mean, that's x bar bar. All values in the table are in minutes. Use this information to obtain 3 sigma, that's z equal to 3, control limits for means of future times. The standard deviation of process is not known. So you have the table here. Don't worry about z equal to 3, that's from the previous formula, but even the table that we see for A2 is actually based on a 3 sigma factor. So please pause here, use the table and use the formula. You can look at the lecture slides for that, and then try to compute the lower limit and upper limit and try to establish the upper limit and lower limit for an X bar chart for this problem, and then come back to see the solution. Let's see the solution for this problem. So the averages and the information that we have in the table actually is similar to before. This is the average for X bar for the first sample, the average for second sample, X2 bar, X3 bar, X4 bar, and X5 bar. And these are the formula here. So we need to compute the grand average, and then we need to find A2 and compute R bar. So let's go ahead and compute X bar bar, the grand average. The grand average we computed before, that's just the average of these sample means. So that's 12 plus 10, that's the first one, plus the second one, plus the third one, plus all of the X bars, and divide them by the number of samples, which is 5. So that divided by 5 is going to get us the grand average, which is 12.11. Next, we need to find A2 here. For A2, we need to look at table 10.3. This is table 10.3. To find A2 here, we need to know the number of observations. So we have 4 number of observations in each sample. That means that n is 4 here. So n is 4, that means that A2 is 0.73. So A2 is 0.73. So we have A2 now, 0.73, and we can plug it in the formula here to find the upper limit and lower limit. But we also need to find R square, the R bar, that's the average range. So the formula for R bar is the average of ranges. So we need to find the ranges for each sample. For the first sample, the range is, that's how widespread your data is. So that's the maximum number minus the minimum number. The maximum number here is 12.11, and then the minimum number is 12.8. So the range here is R1, that's 0.03. I'm going to do it for another one. For example, consider the fourth sample. The minimum value here is 12.08. The maximum value here is 12.12. So the range for this, which is R4, not bar, it doesn't have a bar. R4 here is 0.04 that you see here. So we're going to find the ranges for each of these samples. For the second sample, the range is 0.05, that's 12.15 and 12.10, so that's 0.05. For the third sample is 12.15 is the maximum and the minimum is 12.9, so the average, the range is 0.06, and 0.05 for the second sample. For the fifth sample, the maximum is 12.14, the minimum is 12.09, so the range is 0.05. So if you sum up these and then divide them by n, the number of, divide them by k, the sample, the number of samples, which is 5 here, it's going to give us R bar. So R bar is 0.046. Now we have everything. We have A2, we have X bar, and we have R bar. We plug it in this formula and we compute the upper limit and lower control limit. So the upper control limit here is 12.14. The lower control limit is 12.08. Similar to actually what we computed, assuming that we know the standard deviation was given. The implementation and interpretation of this control chart is the same as the previous example. So what you need to do is you need to focus on the sample averages that you have, and you check to see whether the control limits that you have, these actually averages for each sample would actually fall within this range. The first sample average is 12.10. That would fall within 12.08 and 12.14. So this would be checked. 12.12 would check, 12.11 would check, 12.10 would check, 12.12 would check. All of these sample means are fallen within the acceptable range. So this means that the process is in control and the quality control is passed. But what if actually one of the sample means is fallen exactly on the upper limit or lower limit line? For example, what if actually you have a sample mean here that X bar was, for example, 12.08. So this 0.08 would exactly falls on the lower limit line. Or if it was, for example, X bar equal to 12.14, this would fall again under this line on the upper limit line. Or if you actually had a sample mean that it was outside of this range, for example 12.15, 16, 17, anything bigger than 12.14 would be outside of this range, or it was actually smaller, it was 12.07 or 6 or 11 or 10 or anything smaller than this value, then what we need to do is we need to stop the process and we need to investigate the cause of the variation, because this is a red flag that the process is out of control. For example, it could be that this variation is due to an operator error or to a machine being out of adjustment, it needs adjustment, or any similar assignable causes or sources for this variation. If no source of error or variation is found, then the value could simply be due to chance and randomness, and the process would have to be a startup. The next control charts for variables are range charts or R charts, R bar charts. R charts are used to monitor process dispersion, process scatterness. They are sensitive to changes in process dispersion. The R chart control limits can be computed using these two formulas here. So the upper control limit is D4 multiplied by R bar, and the lower control limit is equal to D3 multiplied by R bar. D3 and D4, they can be found on the table that we have, the table 10.3. And these values depends on the number of observation in each sample n. So let's see an example how we can actually establish a R chart and how we can use it. So let's do the same problem, the problem that we had in the previous example. We want to find the control limits for a range chart for that example. So you have the table here. We have 5 samples. Each sample has 4 observations. You have also the average of each sample, sample mean. So try to use this table and also the formulas. That's the lower limit is D3 multiplied by R and R bar, and the upper limit, this is lower limit, and the upper limit is D4 multiplied by R bar. So find the R bar first, the average of ranges, and from the table using the slides that you have access to, you can find also D3 and D4 for this problem, and then you multiply that by R bar and get the upper limit and lower limit. So please pause and work on this problem before you see the solution. So let's first find the D3 and D4 from this table and the number of observation. So remember, n is the number of observation in each sample. We have 5 samples here and each sample has 4 observation. So n here, to find D3 and D4, n here is 4. This means that D3 is 0 and D4 is 2.28. So next we need to compute R bar. That's finding the range 1, range 2, range 3 for each sample, and then find the average of those and plugging them in this formula using D3 and D4, you can compute the upper limit and the lower limit. So we already computed the ranges here. The range for the first sample is 0.03. For the second sample is 0.05. So we have here, we find R bar, and R bar is 0.046. We have D4 and D3. We plug them in this formula and we get upper limit and lower limit. So upper limit is 2.28, that's D4. D4 is 2.28. 2.28 multiplied by R bar, which we computed here. This is R bar. And we get the upper control limits, that's 0.105. These are in minutes, the time that's going to take for the glue to dry. And for lower limit D3, since D3 is 0, then the lower limit would be 0. So now we have the lower limit and upper limit for the R bar chart. So let's test whether the process is in control based on R chart or not. So we have the upper limit and lower limit. What we need to do is we need to, for each sample, we need to see whether the range for that sample is within this limit. For the first sample, the range is 0.03. 0.03 is between these ranges. 0.05 is 0.06, 04, and 05. So all of them are within the range. That means that the process is in control with the R chart perspective as well. Now you may be wondering which one should you use? Should you use X bar chart for control, quality control, or should you use the R chart for quality control for variables? Well, actually, you should use both of them because there can be scenarios where one cannot identify an out of control variation. So let's see this example. So in this example that you see, this is the sample distribution. These are all normal distribution for each sample. And as you see here, the average of this sample is increasing from the left to right. So if we actually find the control, we establish the control chart X bar for this, it's going to be this. So as you see here, for this problem, we can actually identify an out of control sample. So using X bar chart, we were successful to identify the out of control chart, the out of control sample, and raise the flag that there is something wrong and it needs to be fixed. But if you look at the R chart here, the R chart for this, since the ranges here, as you see, these ranges are equal, although the average is going to shift higher and higher, but the ranges doesn't change. So that's why, as you see here, all of the sample ranges are within the control chart limits, the lower limit and upper limit. So the R chart here would not raise the flag, would actually miss to raise the flag for this. It's incapable of doing that. So as you see in this example, X bar chart could help you, but you would have need to actually run both of them because you didn't know, right? So let's see another example. So in example B, as you see here, this is the process. The process variability is increasing. So as you see here, the average of these all samples stays the same, but the variability increases. The range of variability increases. So if you build and establish a X chart here, X bar chart here, because the average stays the same, all of these samples stays within the range. And the X bar chart would not raise any flag. In its perspective, the process is in control. On the other hand, if you actually establish a control chart, R chart, as you see here, because the ranges, the variation is increasing. So as you see here, the variation increases, the range increases, and this one is actually out of the range. That means that R chart is going to raise a flag here. This is a flag. It's raising a flag, a red flag, saying that the process is not in control. There is something wrong that needs to be addressed. So in summary, we should use both of these charts.